mostly zeros, because some people never, and so I want to fill in that matrix with non-zeros. Okay, so if you think of it as a low-rank matrix, it's to factor that matrix. That's how it's often done. So nowadays, I call it the era of pattern recognition. This is often called deep learning or neural nets or whatever, but it's really just fancy non-parametric pattern recognition. It's good enough that with large data sets, you can run them and do really well on problems in speech recognition, computer vision, and so on. I still think the business model is not really obvious for a lot of these things. Some of them are just surveillance or kind of minimal human services, like I call on the phone and I want to get a little information while they do some speech recognition. It's gotten pretty good, but I don't think the impact is nearly as much as those first two. Right? And in fact, I think we're actually transitioning to something different, which is not so much about third generation, which what people often call it AI. It looks like humans. You're imitating speech and vision. What's, I think, emerging is large-scale decisions in markets and using data analysis to support that. Okay, so this is sometimes called Internet of Things in computer science, but that's kind of the boring problem of just getting devices, every single device to have an IP address and be on the network. Right? But what if now every device that's on the network starts to send data, and you have decisions needing to be made in a completely decentralized, distributed way, millions of decisions, and these are incoherent with each other. How do you make a system like that work? Now, what systems like that exist? Well, the transportation network has gotten closer and closer to that. With services like Uber, right now, in this moment, there is a network being created of people who need a ride and people who supply the ride, and it's all being connected up by software and data analysis. And that data analysis helps put the right number of cars in the right part of the city. It does pricing. It's hundreds of people behind that who do data analysis and economics. The pricing is very important. But think of that even broader. Think of the medical system. Right now there's people in hospitals and various drugs are being tried out on them and various treatments are given and they have various characteristics. Immediately that information should be available to some doctor tomorrow to treat somebody else better. That's how a real system should work, and it should be really done well. It shouldn't be just kind of arbitrary. Out-of-date data should be tagged and so on. That's the kind of system would like to see. Commerce systems are more and more these interlinked systems, and so finance systems and entertainment systems. I think this is kind of what we're seeing emerging. So we need to contribute to this. We need to make these good markets, fair markets, ones that treat all people correctly, one that make human happiness go up. And that's what a good market should do. But it's not just economics, because economics people are very rarely interested in the data. Econometricians are. That's not what I'm talking about. I'm talking about microeconomics, how you design a market. Okay, you have to put numbers in your little tables, your game theory. Where do those numbers come from? What if they're latent variables? What if they're sampling issues, et cetera, et cetera? So blend microeconomics with statistics. Okay, this slide is, I wrote you can't see it, I guess, because of these funny tables. But at the bottom there is a blog that I wrote this past spring. It's called Artificial Intelligence, the Revolution Hasn't Happened Yet. And I usually don't cite my work on my slides, but this one is written for a broad audience, and it's been read by a broad audience. So I put it on a place called Medium, which I didn't even know about, but it's read by a lot of people. I start to read it now, it's pretty good. And it's been read by about 400,000 people, so way more than any academic paper I ever wrote. My orders of magnitude. And it's been read by some very famous CEOs, and they've even contacted me and so on. So I've had an impact that I never had before. So part of it was just trying to say this buzzword of AI is being misused, it's being used as a grab bag for everything, including all of statistics somehow. And it's being used also kind of as a wild card. So you see people like Mark Zuckerberg up there, they ask him, well, how are you going to solve this really hard problem, with either privacy or some aspect of the data analysis? He says, well, AI will do that. That's really not good. So let's just try to break it apart a little bit. So there's what I might call human imitating. This was the original idea of AI in the 50s. That computers are now around. You'd like to see if you could make computers seem more and more like humans, be intelligent. And I don't think we've done that at all. I think we're very, very far from that. What I think has actually happened is something that's called IA. The computer organizes information in a way that makes us more intelligent and more creative. So a search engine does that, right? You don't have to remember all kinds of facts about the world. it's right there at your fingertips. So it's as if you know it. So I could go on about that, but even recommendation systems, all these things kind of around us make us more intelligent in some way. If you didn't know, if you were talking over the phone and you asked me what's the capital of Mongolia, I might maybe pause where I clear my throat, but I'm really typing onto Google and I get the answer back and I say it to you, and so I'm more intelligent. I know the capital of every country in the world, in some sense of know. All right, but anyway, what I think is emerging is partly that, but even broader. It's this, what I'm now going to call II, intelligent infrastructure. So transportation, dwellings, urban planning, large-scale distributed collections of decisions being made in a context of data flows of very, very large scale. Okay? So I think of this as statistics with other aspects to it, but if statisticians don't engage in this, other people are going to do it. And it's data analysis and decision making. They're just going to either reinvent statistics or probably do it badly. So we have to engage with this kind of thing. Okay, so I don't like this human imitating AI. I think this is the one the newspapers talk about all the time, that we're going to replace humans and we're going to have superhumans and all. It's just a bunch of nonsense. And I think it's actually detracting us from these harder problems involving collectives of decisions and how to get good data and make sure its decisions are good and all. So I think that we should spend our time thinking about these kind of networks. We shouldn't think about autonomy. People talk about autonomous self-driving cars as if the autonomy is what you're after. You don't want autonomy, right? You want the car to be networked to all the other cars so that it knows if a tree has fallen down, all the other cars know it. If a kid's just running on the street, everybody knows it. It's a linked system. How do you build such a system? So think about air traffic control. 100 years ago, there was not air traffic control. It was developed, and now we very rarely have a plane crash because of it. So that's what we need. We don't want to ever have car crashes because we want to design a system, not an individual self-driving car. Okay, so here's the kind of things I actually work on as a statistician. Let's call this II, but it's how do you take in big data flows? How do you make multiple decisions? So you can think about this as like false discovery rate. This is something statisticians have thought about more than most people, okay? But a system like Uber in San Francisco right this moment is making probably 100,000 couple decisions. So just false discovery rate alone is not enough, okay? These are not independent decisions. FDR is often independent, okay? So we've got to engage more deeply with the real problem and not just the artificial ones. Systems that create markets, I'm going to talk a bit about that. Uncertainty, we know how to talk about it, but it's hard to do, say, the bootstrap on a million instances, okay? You can't, it's hopeless. So what do you do? Asymptotics? Well, it's very heterogeneous data, it's not meaningful. All these other kind of things look, like computer science, like real-time performance goals. If you're building a self-driving car, you're doing data analysis, but you can't do it over days. It's got to be quicker than that. It's got to be seconds, or less. So statistics has never thought much about real-time data analysis. We should have a temporal budget as part of our data analysis thinking. And then lots and lots of other things. So some of these have a CS flavor, a lot of them have kind of an econ flavor. Explanatory principles, provenance, fairness, diversity. I think there's an econ part of it. Okay, so let's just give an example of an econ issue that if you're just a computer scientist or a statistician, you probably never thought about, but you would be missing the boat. So let's think about decisions that interact, okay? So that seems, of course we think about it. Well, we really don't most of the time. A lot of us are in this IID world. And let's in particular take the example of this recommendation system. So a recommendation system, I already said it. A record is kept of a given customer's purchases. Then we cluster customers and we propose some items from nearby customers, something like that. All right, so that's not exactly how it's done, but something like that's done. Right, but it's being done in the virtual world, online world. So Amazon is an example. If I go to Amazon right this moment, to their website, they will featureize me. They'll turn me into a 50,000 dimensional vector, okay? They will take that vector, all my past, lots of information they have about me, they'll put that into a system, probably a neural net, and out will pop out some recommendations of movies or books or things that I might want to buy, okay? And it's not too bad. So, maybe then later on the day, someone else in the room will go to Amazon and they'll featureize that person, that'll go into the same network and out will come some recommendations. All right, now there's a good chance they're going to recommend the same items to me and that other person. In fact, it's Amazon, so the scale is, hundreds of millions. So there's a good chance they'll recommend the same thing to huge numbers of people. Okay, so what if they do that? What if they recommend the same movie to everyone? right? Well, that's the classic setting of a recommendation system. You're in the virtual world, so there's no scarcity, so you don't need any econ principles. You can just copy the bits as many times as you want and stream them to everybody, right? That's the kind of mindset, right? What if you recommend the same book to everyone? And again, everyone means, you know, like a few million people, and that's good. I'm sure that happens, you know, in very many days at Amazon. Okay, so that starts to be a little scarcity. I don't have all those books on hand, all right? But you can do something called print on demand, and you can print them probably within 3 days, and you can get the books to people, okay? Okay, but now let's think about a more serious thing that's not just classical Amazon. Let's think about a system that's going to recommend restaurants to people. Okay, now I don't mean just on my browser there's a list of restaurants or some advertising scheme or something. I mean something economically viable and interesting, of the kind we probably don't even have yet. But suppose I go to Shanghai, I had a bunch of meetings all day, and it's now 7 p.m. and I'm by myself, I walk out, and I'm hungry, and I'd like to go to a restaurant, okay? I don't read Chinese, so what I want to do, I don't want to go to my computer and start browsing Yelp or whatever. I want to push a button, just like I do for Uber, announcing to my surroundings that I'm here, I'm geolocate me, and I'm hungry. And so it should already know something about me. It's a recommendation system, so it should know something about me. So it should tell the restaurants that I'm nearby and that I'm interested in being a client. Okay, so then the app in the restaurants should look at me. It's a two-way market. It's not just a platform where I'm getting a service. It's a connection between producer and consumer. They should look at me and they should say, well, I see he likes Sichuan cuisine. He's in this location. He's kind of nearby. He's a certain age group or certain whatever. We like him as a possible client, so they make an offer to me. Say, you know, if you push your button again for in the next 10 minutes, you'll have a 10% discount. So then, being on my phone, I see an offer, and I look at the restaurant, and it's close by, and I like the look of it, the food, and everything, so I accept. So we've made a transaction, okay? And now I go there. Compare that to someone who builds a recommendation system for restaurants, which there are tons of companies who are doing this. Right? And so they will broadcast to anybody who happens to be in Shanghai a list of, you know, here's a restaurant to go to. And there's a good chance they're going to recommend the same restaurant to 100,000 people. Okay, if this app is widely used. If it's not widely used, who cares? But when it's widely used, and everybody goes there, and there's a line. So there really is scarcity here. You don't solve it by building a better app, right? So a lot of these companies, that's what they're effectively trying to do. They're trying to say, well, we're not really creating a market. We're just trying to provide a service to people. We don't know what the people will really do. Will they all go there? So we'll try to figure it out by their browsing history or other latent variables. Okay, that's hopeless, right? You don't need to know much of it, be much of an economist to know we cannot know those kind of things about people. So instead, I build a market. Okay, now there's a market between me, our clients, and the restaurant. The restaurant will not offer 10,000 people to come to the restaurant. Okay, if they do, they will pay the price. Everyone will come there and will be mad. So it's so easy, just build that, right? Now, is this statistics? Yeah, of course it is, because you have to do a recommendation. I don't want to just look at all restaurants in China. I want the ones that are interesting to me, just like when I go to Amazon, the books I might like, right? And similarly, the restaurants don't want to have all possible clients. They want ones that they kind of would like to have in their restaurant, okay? Now, of course, there are legal issues here about who do you serve and all that. Lots of interesting things come up when you do this, but really the main point is that human happiness will go up. I will get the dinner I want, the restaurants will be full, human happiness will go up, okay? And then we have other problems to solve. Now, let's build other kind of apps. Let's build apps that try to get people from some place to some other place as quickly as possible. So I need to go to the airport later. I don't, I suppose I do. You know, I should go to my app and say airport, and it should give me a proposal of a route to take. Now, if I'm the only one using the app, no problem. There's no scarcity. But if 1 million people are using the app in San Francisco and they all try to go to the airport, there's a good chance the app will send all of them down the same road. Because it's just a recommendation system. That's what they would use, the off-the-shelf software. And when all of us are sent down the same road, it's no longer a good road. Okay, so again, how do you fix that? Well, you can try to build a super application which tries to balance the streets somehow between people, or decide who really needs to go there, or whatever, do something even worse. But what you really do is just build a market, all right? So essentially, every street segment should make a bid to the person who wants to go down that street segment. And then I will have some interface where it'll say, well, how desperately do I need to get to the airport? How quickly? If I really need to get there quickly, I'll pay more in some currency, whatever that currency is. If I don't need to go so quickly, I will pay less, and I will save money for the next time I'm in a rush. Whatever. I don't mean really money, but I mean some economic, it's part of an economic system of some kind. Points. Okay, here's my favorite example, is that I have spent a lot of time in China recently, and a lot of people have money that they never had before. Like a grandmother has $1,000, and she'd like to invest that money, but she has no idea how to do that. So there are apps that spring up, fintech, that are trying to propose, here's how you invest. And that app might propose for her to buy Alibaba stock or something, okay? But that same app is just a recommendation system. Someone downloads some software and it's doing recommendations to people. It can easily recommend to 100 million people to all buy Alibaba stock, all right? And Alibaba stock shoots up, artificially destabilize the market. And so this is a big concern to the Chinese government. People talk about regulations in China, this is the kind of thing they have in mind. Okay, so we have to deal with this, and really the way to do it is to think about market creation. And you can pick up economics books and learn a lot about making markets. It's called market design, and there's a lot of principles and ideas and all that. And I'd say that in 100 years we'll look back and I'd say that was the germ. But that's probably gonna be like 1/10 of all the kind of markets. Because these new inferential type markets that I'm thinking about are gonna require new kinds of ideas. Okay, it's not gonna be classical markets. Right? And we talk a lot about fairness, and people talk about all these learning systems, predictive policing or what have you. Is it fair? Well, fairness is hard. It's just not just a trivial matter. But a lot of people are talking about, well, fairness just means the system gives the same output for everybody, or the same marginal probability for everybody, or something like that. That's not fair. Fairness is that I'd be able to say what my utility is, what I want, and then my utility is respected by the system in some market sense. I'm not going to get what I want, right? But I want a balance, right? That's what markets should do. So if we don't even talk that language, we're not going to even be able to talk about fairness in any way. Now, that's not all there is to fairness, but that is part of it. I mean, if you love yellow socks and I love red socks, I really don't want to be proposed the same socks as you're proposed. Okay? It's not what I want. It's not fair. Okay. Let's see. I'm going to think about my time a little bit here. So this talk is in two parts. The first part is what I'm doing right now. It's just kind of some thoughts. Why do I work on the kind of problems I work on? The second part is the math. How does this lead to actual research? And what do I really do? You have talks, right? I have opinions. So I think I'm going to skip over this next little bit here because I want to spend a little time on, these challenges. So I want to spend some time on what kind of things I really do. So if I'm telling you that this is statistics, well, what do we work on? Okay, so actually this slide is kind of what I think of what we work on. So things like this. I've now talked a little bit about creating markets and a little bit about multiple decisions. And every one of those is something I've been working on in the last 10 years, and I could dig in. What I'm going to do instead is say that behind all of those things, there are some algorithmic challenges. And they aren't just run linear regression, okay? They're not even penalized for this or that. There's some new challenges. All right, so I'm going to turn the talk over now in a very different direction, and I'm going to talk about algorithmic, mathematical, and statistical challenges, right, that are new. And I'm going to be a theoretician here mostly because I think that the main point of doing this is kind of to say what are the principles and not just try things out, but if we're going to be academics, we need to have some principles. So I'm going to talk a fair amount about non-convex optimization. It's less familiar than it should be to statistics, but it's emerging as a very successful algorithmic and mathematical area, particularly focusing on saddle points and dynamical systems that avoid saddle points. At the end, I'm not going to probably have time, but this is my now focus is market design, as I've been talking about. And there, you want to not avoid saddle points, you want to go to saddle points. Those are the things like Nash equilibrium. Those are good, all right? So how do you design algorithms that will go to good Nash equilibrium and avoid other Nash equilibria and avoid other saddle points? And then we're going to talk about sampling, especially if you're Bayesian, you're really not content with just optimization, you want to sample. How do you do that efficiently in high dimensions when things are not convex? There's been very little work on that. All right, so my talk I've been giving the last 10 years is I focus on this relationship between computation and statistics. That there's a very ad hoc, distant embrace that most time data analysis actually has a time budget, but we've not, in statistics, we've acted as if that doesn't have, that's not the truth, the case. So if you're doing finance, you have a time budget of milliseconds or even microseconds in some cases. If you don't do it that quickly, you lose. So hedge funds hire statisticians and they bring them in and say, great, use your thinking, but you've got some new things to learn, how to make this run fast. Search on the internet or advertising placement, that's kind of milliseconds. When the markets are running that fast, you do a data analysis and you have to turn it around in milliseconds. But even something like medicine, especially if you start doing personalized medicine, you're going to want to have the results of some data analysis within minutes to hours, or someone might die. Okay, transportation, seconds to minutes before something bad happens, and so on and so forth. All right, so we all grew up in an era where you got a data set, and you were allowed to sit on it as long as you wanted, and the scientist eventually you got back the analysis, and that could take months or a year. And that's just not that still exists, but it's just not what we should be mostly focusing on. Okay, now it's hard because if you look at statistical decision theory or even any statistical, you never see the word runtime. There's just not that concept there. So putting it in is not trivial. In computer science, they certainly have runtime in their theory, but they don't have statistical risk. They don't think about populations and inferential statistics. They just don't. So this is a challenge to put these things together. In trying to meet this challenge, optimization theory has provided a big help. It has been focused, because we're at large-scale problems, on just gradient-based methods. When I learned optimization, it was in the 1980s, and it was all about Hessians and conjugate gradient, very fancy techniques. They had beautiful proofs and nice software, but they don't even come close to working in the modern world. They're way too slow. So using gradients, and not even gradients, but stochastic estimates of gradients has turned out to be critical. And then also understanding how fast you can go. You would like to know when you're done on some problem, can I do any better? So getting lower bounds has turned out to be really important. Okay, so now let me finally tell you about an actual project to give an example of things we really do. A bunch of colleagues around the world. Jin is a student with me at Berkeley. And I'm going to tell you a little bit about how to escape saddle points efficiently. What do I mean by that? Okay, well, a lot of our problems are non-convex. The loss function is not like least squares where I have a bowl-shaped quadratic. It's non-convex in some way. So certainly things like mixture models give you this, but I'm going to show you a list of problems where it's all a bunch of non-convex problems. In fact, lots and lots of eigenvector kind of problems are non-convex. So in 3 dimensions, a saddle point might look like that, but now we're working in real-world problems with millions of dimensions. All right, so think of a saddle point lying there in middle interdimensional space somehow, and it's oriented in some arbitrary way. And as I approach it, most directions out might take me back up again. And there's going to be some direction that gets out, and it may take me a long time to find that. And in fact, if you watch as you do parameter estimation in a lot of these really large-scale models, what happens is that some kind of error of some kind comes down very quickly, and then it plateaus out. And you might think you're done. In fact, if you wait an hour, even a day, it stays plateaued. But then if you wait another day, it goes down again, and you get a much better result. So what's happening is you've found yourself near a saddle point, and it took you a long time to get out. All right, so we want to get theory that says how fast can you get past saddle points, and we specifically don't want to just have a rate. We don't want an asymptotic rate, that's old-fashioned. We want a real rate, meaning for any particular finite amount of time, how long is it, how close are you? But even more than that, we want dimensional dependence. Okay, so this has been missing for most theory in most fields. It's just the dimension dependence is not even talked about. But if the scale is exponentially in dimension, these items are going to die. We're not going to be able to really deploy them in real life much longer. If it's even polynomial, that may be a problem. So what is it? All right. Before I get to that, here are some non-convex problems. Some of them should be familiar: principal component, canonical correlation. Some of them are less familiar: phase retrieval, dictionary learning, matrix sensing, and all. But these are real-world problems used in sciences and technology. They're all non-convex, but they all actually don't have any local minima. They have one single global optimum, and then they have rings of saddle points. And the saddle points are the whole trouble. So if I start up here, what I'm going to do is go past a bunch of saddle points, and I might get sort of stuck for too long. So what can I say about that? Okay, so we've been working on this for a little while now. Here was a little background. Gradient descent will asymptotically avoid saddle points. We showed that 4 years ago. That was not known. But that's an asymptotic result, and we're not at all really interested in asymptotics. That was just kind of to get us started. Moreover, gradient descent, we had a paper that showed takes exponential time to escape saddle points. Okay, that's bad. Right? But we already knew from a really nice paper by Good et al. That stochastic gradient can escape saddle points in polynomial time. Right? And that's kind of hints that stochastics is necessary and sufficient, but also hints sort of why it works. It's not exponential time to avoid saddle points. Somehow it gets out of the polynomial time. And when you know something is polynomial time, you might hope to go, first of all, what degree? Is it d to the 45th power? Is it d cubed? Both of those would still be bad. But is it linear? That might be really great. Okay? Well, that result didn't tell us. So we were really curious. Okay, so here's a convex function. Let's start with that. And here's gradient descent. Hopefully you all know gradient descent. You can prove with not too much work that this converges to a global minimum. It's like 2 pages of proof. But the most amazing part of it is the number of iterations to arrive at the global minimum is independent of the number of dimensions you're in. Independent. You can run this in infinite dimensions and it's just as fast as in finite dimensions. So that's an amazing fact about gradient descent. So here's an example of a theorem. There's a theorem right down here at the bottom due to Nesterov. The Russian school has read a lot of this work in 1998. So just briefly, you make a smoothness assumption. It's called gradient Lipschitz. Instead of asking that the gradient vanish, that's classical stationarity from calculus, you put a little epsilon ball around the gradient, around the minimum, and then you solve these equations for a varying epsilon, and that gives you a rative approach towards the optimum. Okay? And here is the rate. It's 1 over epsilon squared. Okay? So that is a rate. It's not an asymptotic rate. Okay? And it says that if you've taken, this is the number of steps it takes to hit a ball of size epsilon. And in fact, there's no hidden constants. There's the Lipschitz constant L, and there's initial distance to the optimum, which has to be the case. If I'm starting really far away, by bad luck, it'll take me more time. Okay, so that's the amazing kind of result we want. First of all, there's no dimension dependence. No D is in that formula. And there's no hidden constants of any kind, and it's not asymptotic. So when we do theory like that for this kind of situation, okay, so now sure the math is going to be way harder. It's not convex. It's going to need some topology or differential geometry. If we run gradient descent on this surface, it's going to hit a first order stationary point, which could be a saddle, or it could be a local maximum, and we wouldn't know. It stops at those points. Okay, so first of all, we need a criterion that rules those out, and secondly, we need an algorithm which will minimize according to that criterion. Okay, so here's the criterion. It's called second order stationarity. It's pretty natural. You just ask that your first order stationary, and you ask that the minimum eigenvalue of the Hessian is greater than or equal to 0. That would get you a bowl-shaped thing, so no saddle points. And instead of using 0, again, we give ourselves a little ball around that. So negative something is a little bit of slop. Okay, so we're going to analyze not gradient descent, because we know that takes exponential time, but a perturbed form of gradient descent, where you can't see it, I think, but it's just gradient descent is line 4. And line 3 is that sporadically, whenever the gradient is small, you add uniform noise from uniformly from a ball of size r around the current iterant. Okay, and you do this sporadically. You don't do it more than once every capital T steps. So we've introduced 2 new parameters, T and R, but the theory tells you how to set those. Those aren't free parameters. Okay, so analyzing that in the non-convex setting, we would ask to get a rate, and we're able to get a rate. And this was a lot of work, but this is the final result. So under the setting I've told you about, the number of iterations to hit a second order stationary point, in other words, to avoid saddle points, is 1 over epsilon squared. So we didn't get any slower in this non-convex world. That's pretty amazing. And moreover, just Lipschitz times the initial distance. The only difference here is that little twiddle, which is traditionally used to hide dimension dependence. Okay, I say we don't know. But I'm going to now be honest and tell you the dimension dependence. It's logarithmic to the 4th power of d. Okay, so it's not polynomial at all. It's way, way better. It's logarithmic. Okay, so that 4 is, I don't think, true. I think that's an artifact of our proof. I think it's actually logarithm. But the proof is hard. And I think, and we don't know yet how to get rid of the 4, but still, who cares? Logarithm of the 4th power is not bad. Okay, analyzing this kind of thing requires some mathematics. So this field has got some new math that's needed, okay, and this was new math. Around a saddle point, there is a region in which, if you're in that region, we call it the stuck region. If you're in that region, most of the flow is toward the saddle point. You're not getting out anytime soon, okay? So I need to know the width of that stuck region, because if I'm out of that stuck region, then the negative eigenvalue kicks me out exponentially quickly. So how do you analyze a region like that? What calculus do you use? Well, this is essentially differential geometry, but it's hard. And it's, this whole thing is a pancake, but it's curvilinear because the Hessian is varying in the neighborhood. Okay, so we're not able to do the differential geometry here, or at least not easily. So instead we use probability theory. And so here's the probability theory approach to this problem. You start two coupled diffusions at distance r apart, where r is going to vary. If your r is really small, those two coupled diffusions will hit each other pretty quickly because they're both flowing towards the sound, so they'll couple. If the r is a little bit bigger, those two diffusions will fly apart because of the negative eigenvalue. So you could try to calculate the coupling time of two diffusions, and there's a phase transition in the coupling time. When you find that phase transition, that's the width of the surface. Okay, so that's fun mathematics. So when you do that, you get the logarithm to the fourth power. Okay, so now we can ask really interesting questions like about, we got a rate now, and it looks pretty fundamental. There's no hidden constants or any kind, and it's not as about. Is this the best we can do? Are we done with this field? Okay. Okay, so kind of amazingly, in optimization theory, there are really meaningful lower bounds. So this is not true of most fields, at least I work in. Most fields don't have any lower bounds. Fields like computer science have some lower bounds, but they're too low. There's a big gap between that and the actual algorithms that are out there. Statistics has some lower bounds, but not that many. So Kramer-Rao is a lower bound, but it's not all that useful in the modern world. And we have a few other lower bounds in empirical process theory, but we're not a lot. But optimization has some interesting lower bounds. Okay, so this project this opened up everything else we've done. So this is a variational Hamiltonian symplectic perspectives on something called deceleration. So that's a whole talk of its own. I'm just going to give you a couple of highlights, because it sprung many other results for us. So I can let you know that this line of work happened, and I'm going to give you a little rough flavor. The two grad students on the left working with me in Berkeley were critical in this. Andrew Wasona and Aisha Wilson, both their theses were on this. They worked together. Andre's first contribution was some of this Lagrangian, and then Aisha worked on the Lyapunov theory for this, and had a number of very, very striking new ideas that helped us later. And then Mike Betancourt joined us for the symplectic part of this. Okay, so let's go back to gradient descent again. Here is gradient descent one more time. Let's suppose we're again back to the convex domain. And let me add a fact about this now, which is that this algorithm converges at a rate of 1 over k for convex functions, meaning after I've gone for k steps, I will be guaranteed to be in a ball of size 1 over k of the origin. Sorry, the origin of the minimum. Okay, so that's interesting. Now you can ask, is that the best you can do? All right, so that's a lower bound question, and it's a complexity theory question. On this class of functions, how complex is this problem? All right, so at the Russian school in the 80s, kind of when everybody thought that optimization theory was kind of dead, there was not much left to do, started to ask questions like that and kind of broke the whole field open again. Arkady Nemirovsky and others said, well, I'm going to define a notion of complexity that's appropriate for optimization. What I'm going to do is say, I have a machine that's allowed to look at the gradient of a function and all previous gradients that it's seen. It has a memory, and it has to step within the linear span of all those gradients. So that's gradient descent, that's conjugate gradient, that's a bunch of other algorithms. And now you can ask, on that machine, which is not like a Turing complete machine, it's limited but still powerful, what's the best rate I could possibly achieve for convex functions? And he proved that it's 1 over k squared. So it's faster than gradient descent. So it's kind of interesting. Gradient descent seems, if you're only going to get to look at gradients and previous gradients, how can you do better? It's steepest descent. Okay. Maybe this lower bound is just too low. Maybe it's an artifact of a bad proof technique. So it came as a shock, I think, to many people when another Russian, Yuri Nesterov, proposed an algorithm that's got two pieces to it. Y is like a gradient descent, and then X is a linear combination of the previous two Y values, so it's a little more dynamical. And he analyzed that algorithm and proved that that algorithm goes at rate 1 over k squared, and it's only looking at gradients. So this is called accelerated gradient. It's been like 30 years of research on this, and many areas of optimization have been changed very deeply by this kind of style of work. It is, however, not really understood to this day where this phenomenon is coming from, why it happens, what it means, and how to do it. It's just kind of an algebraic flurry of tricks. All right, so Andre, Aisha, and I worked on this, and our perspective is that the right way to think about this is as a continuous time, okay? If you're hopping along a set of points and you ask to hop faster or hop at the optimal speed, that doesn't really mean very much, okay? You have to have the problem embedded in a continuum to talk about going faster, okay? So anyway, we took the problem into a continuum. I'm gonna just skip ahead here and show you, I wanna just show you the work we did. We turned this problem into a continuum, and we wrote down an object which we call a Bregman Lagrangian. This is, if you know any physics, it's a Lagrangian. It takes a Bregman divergence between x, where you currently are, and x plus a time-scaled x dot. So that's a distance measure in a phase space, and it subtracts off the function you're trying to go downhill. Bregman divergences have what's called auxiliary function h that helps to measure distance. It's like Kolbeck-Leibler divergence, that would be the logarithm. For Euclidean distance, it would be square. If you set h to quadratic, that first term reduces to 1/2 x dot squared, which is kinetic energy. So it's very much like kinetic minus potential. It's a Lagrangian. Okay. So what we were trying to do was, like, Lagrange, I think, originally did. He looked at the equations of motion, like F equals ma, and said, that's an interesting differential equation, but why that differential equation? Where did it come from? Is there an underlying energy that it's minimizing? And that's what Lagrangians are. So he also helped develop variational calculus. He put the Lagrangian inside of an integral and then minimized over paths. And doing that, the sufficient and sometimes, or the necessary and sometimes sufficient conditions are Euler-Lagrange equations. And if you do all of that for that Lagrangian, you get a second order differential equation at the bottom of the page. And that is a master equation. So all known accelerated gradient methods in continuous time are reflected inside of that equation. Okay? So that'd be a longer talk to convince you that, but it's true. Moreover, the Lyapunov theory that Aisha developed showed that we can get a convergence rate of this once and for all and characterize convergence on all kinds of classes of problems. Right, so this has been critical for all the work we've gone after since then. And at this point, a very, very interesting thing happens, which is it turns out in this continuous time formulation, you can go as fast as you want. There's no upper bound or lower bound. Every algorithm, though, that is good in some sense follows the same path. They just go on a different rate along the path. And so it's as if you have different clocks, right? But good algorithms follow the same path. Now, when you move back to discrete time, you try to approximate that path, but you also want to move quickly along the path. And we know, however, there's a lower bound in discrete time. You can't move too quickly. So it must be that discretizing the differential equation is the problem. That this is a class of differential equations which, for some rates, you could discretize it, and other rates you cannot. There's a phase transition. Okay. So we have been working on that for the past year, and symplectic ideas, if you know anything about these, have turned out to be helpful here, and I'm just going to kind of skip this. I just want to tell you that this stuff works. If I start with a problem formulation, here's a loss function, and I give myself a desired rate, then everything else is mathematics after that. That turns into an Euler-Lagrange equation, into a differential equation. Symplectic integrator takes the Hamiltonian version of that and turns it into an actual algorithm on the computer. You run that, and it beautifully does things like goes downhill at the oracle rate. Okay. These algorithms actually don't just go, they're not descent algorithms, they go down and up, which is kind of amazing, but it's a fact. The fastest algorithms don't just go downhill, they go down and up. Moreover, if you compare this to the best existing algorithm, which is this Nesterov acceleration, this famous algorithm I showed you earlier, they're basically the same. This is for a different class of problems, but they're actually better because if you turn up the step size, if you'll see if I go back here, oops. I've moved over to the left. I've turned up my step size. Nesterov goes unstable, and this new approach stays stable. It's part of the magic of symplectic integrators. Where have symplectic integrators ever come up in statistics? Before this, well, they have. If you know about Markov chain Monte Carlo, the world's best algorithm by far, and they put in the Stan software, or what are called hybrid Monte Carlo. And hybrid Monte Carlo is using a leapfrog integrator inside of Monte Carlo. Leapfrog integrators are symplectic. Okay, So with all of that, we were then able to do a whole bunch of other things that kind of helped to solve some of the problems I was talking about earlier. So let's just try to line up a couple of them. I'm going to show like 3 or 4 more parts and then finish, where there's like 1 page on each one of them, just to give you a flavor. So one of the first things we did is to ask, well, what if we put these 2 things together? Let's do acceleration now in the non-convex world. Mostly acceleration has been studied in the convex world. Can we accelerate? Does acceleration help us to get past saddle points? Okay, so here I am on all these saddle points and I'm trying to get past them. Does it make sense to try to use accelerated algorithms? Or do they get worse? Do they actually not? Do they get stuck in saddle points? That's been an open problem. Well, it turns out that this whole approach, this Hamiltonian and continuous time approach, allows you to solve this problem. And the answer, here's the theorem, is that the rate now goes from epsilon squared down to epsilon to the 7/4. That's faster. Okay? It's actually meaningfully faster, but the main point is that it's faster. It's not worse to accelerate. So acceleration is good for non-convex problems. It's better. Okay? Okay, now let's turn to the part that's really more closer to where my current research interests are. Everything up until now has been just algorithms with deterministic differential equation stories. What if we have stochastics? Because we have sample data, or because we're adding random noise to make our algorithm, like a Markov chain Monte Carlo algorithm. So here, this is with Shang Chen, Neil Chatterjee, Peter Bartlett. We asked the following question: can you accelerate a diffusion? All right, so what's a diffusion? It's just like a Brownian motion transformed in some way. Okay. So Brownian motion, it's part of our statistical heritage. It's used in finance and physics, right? But mostly it's just been used as, here's Brownian motion, and it kind of looks like it wiggles like the stock market, right? And if you transform it, it looks even more like the stock market, but it's just a modeling tool. I'm not aware of research that asks, is there an optimal way to diffuse? If I'm trying to get down the hill as quickly as possible in a high-dimensional space, are some diffusions better than others? Is there an optimal diffusion? Okay? And physicists seem not to have asked this question either. Brownian motion came out from the pollen on water, and it was just a phenomenon. There was no attempt to make it, how fast could that go? All right, so in fact there have been some negative results, but they've been focused on one kind of diffusion, which is the one used mostly in Markov chain Monte Carlo literature. It's called overdamped. We're going to take diffusions which are underdamped. They're more oscillatory diffusions. They're not just standard Brownian motion. And they, in fact, are going to be faster than the classical ones. Okay, so hopefully some of you have seen stochastic differential equations. If you haven't, don't worry, it's not that important. But it's I'm using U now instead of F. And so I take the gradient of the function I'm trying to go downhill and I add some Brownian motion. So this is like gradient descent, but with some Brownian motion. It's called Langevin diffusion. Does this thing have a rate? So this has been studied by the physicists for like a century, but does it have a rate? That's new. So Dalalian in Paris started this line of research in 2014, and he got a rate. He showed that in total variation, Pn, which is your current probability distribution of your current iterate, approaches the stationary distribution at rate, a ball of size epsilon at rate 1 over epsilon squared. Okay, so that's this right here. Okay, so the rate is not worse than gradient descent. So in that sense, stochastics is not slowing us down, but the dimension dependence is deep. That's not so good. That's not logarithm. That's not so good. So that's where the stochastics is in some sense hurting us. That's the penalty we're paying. Okay, we said, can we go faster? Well, let's let ourselves have 2 equations, not just one. Let's underdamp this thing. All right, so we now have our gradient in the velocity term and our Brownian motion too, and then we integrate the velocity to get the position. So this is a second order SDE. Okay, and now we do the theory of this and get a convergence rate, and here it is right here. The convergence rate is now 1 over epsilon, not epsilon squared, so that's way better. And moreover, the d goes to square root of d, which is also way better. Okay, so this is a much better MCMC kind of style, is to put oscillatory dynamics in your MCMC. You don't lose anything, you get the same stationary distribution, but you get downhill much faster. We don't know a lower bound. We don't know if that's the best you can do. I think it is actually, but we don't have a proof of that yet. The underlying proof idea is something called reflection coupling. So if you're a probabilist, there's just a whole bunch of room for more probability ideas. It's just borrowed from probability. So instead of having 2 Brownian motions which couple at some point, You take one Brownian motion, you take a mirror, and you reflect that through the mirror. And now you take the one-dimensional line between them and take its norm. Okay, that's a stochastic process. And now you use Ito calculus. You take the d of that norm between the two reflected processes and just do Ito calculus. You find the drift and the fluctuations, and you analyze that in the same kind of way I've been talking about, and that's where we get. So we turn this high-dimensional problem into a one-dimensional problem with this use of reflection coupling. Okay, this is the last little bit, and I'm going to conclude. This is my most favorite one of all of them. This is kind of amazing. So Yian Ma is a postdoc with me at Berkeley right now. And he has a very strong applied math background, and he's a sampling guru from kind of the physics literature. So he wanted to understand the relationship between what he knows and all this optimization work I've been telling you about. All right? So the folk wisdom is that sampling is slow, like MCMC is slow, whereas optimization is fast. All the machine learning people use optimization. You know, Bayesian statisticians use MCMC. Right? And Jan said, well, is there a theorem on saying that? And people said, well, no, but oh, for the convex case, yeah. But he says, well, that's not the interesting case, not in the modern world. So he says it's really true. Okay, so here's a theorem. I got 2 slides of the theorem. Let me just slow down. I didn't want to have a lot of slides in this, so I'm just going to take a moment to show you this theorem, which is kind of amazing. And I'm going to just point on the important part. Okay, so this is a class of functions which is non-convex, but it's in a particular way. It's like a mixture model. So inside of a ball of size r, it's bumpy. It's not convex. It goes up and down. Okay, because you have kind of this. We don't know. It's multimodal. Outside of that ball, it's strongly convex because a prior kicks in and makes it smooth outside of the ball. Okay, so on that class of functions, how fast can you mix? All right. So mixing in the MCMC world is measured by a mixing time, how long it takes until you're at the stationary distribution. So Jan was able to bound the mixing time of 2 algorithms. One is called Metropolis adjusted Langevin algorithm. The other is unadjusted Langevin. There are just 2 versions of the Langevin I just told you about. Let's focus on the one at the bottom. So forget all the other elaborate stuff here. Just look at the epsilon dependence first of all. It's 1 over epsilon. That's really good. But it's even way better. It's logarithm of 1 over epsilon. That's called linear convergence. It's super fast in epsilon. What about the dimension dependence? Well, there's a d to the 1/2 there and a d to the 3/2 inside. So it's d to the d squared. Okay? So that's not so bad. It's polynomial. It's not great, but it's not polynomial on a pretty complicated function. Okay, anyway, that's for sampling. Now what about optimization? So let's just unleash some optimization theorist on this class of problems. How good can that person do? Can they beat this? All right, and here's the amazing theorem that Jan proved, which is that he said, I'll let you have any optimization algorithm you want in this class. You can look at gradients or even higher order gradients up to Hessians or whatever you want up to the nth order gradient, right? And I will show you a lower bound on the amount of time it'll take you. You have to take at least this much time. And the lower bound is exponential in dimension d, okay? So sampling is polynomial, d squared. Any optimization algorithm must be exponential in d. Okay, so I think no one had any idea this kind of result existed. It's very surprising, and we're kind of still puzzling through the consequences. And I had a couple other bits, but I think I really want to finish up at this point. So just let me tell you a couple of new students well, Lydia's new, and we're working on the following little fact. Everything I've been talking about here is with these smooth but non-convex problems. But in statistics, when we sample, if that's the population loss, the risk, when we sample, we get this little speckle from the sample. And if we naively apply gradient methods to the thing on the right, we're just going to get stuck immediately. All right? But all these algorithms are stochastic gradient. So do they get past those little bumps? Can you quantify that? And so Lydia and she have done that and have a paper quantifying all this, and there's a very beautiful result of that. In fact, it completely characterizes the problem. All right, anyway, this is what I'm going to be doing for the next year for sure, but probably the next 10 years, working on market design meets gradient-based learning or estimation. And I've got 3 great students. I've already started some projects. We already have a couple of papers. Lydia, Horia, Mania, and Erica. Okay, so let me finish up. People talk a lot about AI and intelligence. I just want to say one remark about that. If you're up on Mars and you're looking down at the Earth and you say, what's intelligent down there? If you had computers up there, what should we try to imitate down on Earth? Well, everybody notices that these things called humans seem to be kind of intelligent. They have a brain, and it's somehow leads to intelligence. Right? So you can try to imitate them by understanding how the brain works, or doing psychology. Right? But that's not the only thing that's intelligent on the planet Earth. What else is intelligent on the planet Earth? Well, animals to some degree, but let's forget that for a moment. What else? Anything else? Is that it? I mean, the climate is arguably complex, but not really intelligent. So is there anything else? Okay, so yeah, think about the city of San Francisco, and think about every restaurant and every home. Every restaurant has some dishes that it makes, and it needs ingredients for that. And that food has got to come into the restaurant every day. And that food comes on trucks and buses and trolleys or whatever from who knows where. And it happens for every restaurant and every home and every store. Not too much, not too little, more or less. And it works. It's robust, it's adaptive, no matter what the weather, the conditions. And it works not just in San Francisco, but in every city around the world. Okay? Those are systems. They are intelligent systems by any definition. Okay, so if you want to think about intelligence and make the computers that we have in our lives more intelligent, you should also think about this kind of market intelligence. How can we mimic that and get the good out of that and make computers part of a market intelligence? So if you really want to use this phrase AI, which I do not like, I would say at least it's data and algorithms, i.e. statistics, but also economic or microeconomic thinking is needed to make these algorithms actually deliver good things for people at scale. Okay? Balanced utilities. And if you're trying to build IT business models, so in a longer talk when I go down to Silicon Valley, I tell them the following. People like Google, or companies like Google, are providing a service that no one is willing to pay for. Search, or Facebook, social network. No one really, it's not so good that you want to pay for it. So no one pays for it, and they make their money off of advertising. So instead of trying to link producers and consumers of information needs, and then have some transactions being made and take a cut of that, like Uber does with transportation, they just use advertising. And that has led to many of the headaches that we're seeing nowadays. Mark Zuckerberg doesn't get it because this is his only model. It's the only way he can make money. Right? And I don't see he has any way out. Right? So instead, think about other companies like Amazon. I think is a better example. They create a market. They create links between producers and consumers. They don't do any advertising at all. And people are happier because they're getting a package on their door or some sort of valuable thing. People are happy with Uber, gets you to where you want to go. And Uber doesn't do any advertising. Okay? They just take a cut of the transaction. So I think that's a better way to go, and I think that's, if we're, as statisticians, if we're going to think about contributing to this world, don't just go out there and help the advertisers advertise. Help the market builders build new markets. Okay, thank you.
So let's give a round of applause again to our keynote speaker. Wonderful presentation. All right, so I think dinner is almost ready. So I think we're going to start dinner, and then by